तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
The question raised was just as we have a phase transition from a paramagnet to a ferromagnet, do we have a phase transition, a corresponding phase transition in the case of an electric field? Are there substances with permanent electric dipole moments in the bulk, just as there are permanent magnets with permanent magnetic moments in the bulk? And the answer is yes, these are called ferroelectrics, and this is called a ferroelectric transition, pretty much the same as ferromagnetic transitions, but the mechanisms could be slightly different, and generally ferroelectric transitions are also accompanied by structural phase transitions, namely there would be crystalline phase transitions which would lead to shapes of unit cells or whatever which have permanent electric dipole moments, but they fall in pretty much the same kind of class. As we will see, even the magnetic transitions, there are huge numbers of them, many numbers kinds of magnetic transitions. We are trying to look at the simplest of these. So that brings us to where we were. We were trying to make an analogy between fluids and magnets, and in the process we had to write down the equation of motion, or the equation of state for a ferromagnet or for a magnetic substance, which connects the magnetic field, the magnetization and the temperature, just as for a fluid the equation of state connects the pressure, the volume and the temperature. So this is where we were at, and we had reached a stage where we said that the magnetization M in a simple model, an up down model for instance, was of the form n mu tan hyperbolic. If you recall, it was mu times the external field over k Boltzmann T. This was a typical equation of state between M, H and T for a paramagnet, but in the case of a ferromagnet I pointed out that you had to modify this by writing this as H plus lambda over n times M itself, namely an electric field in a magnetic field, an effective field that is proportional to the magnetization itself, in some kind of approximate treatment of the internal field inside a ferromagnet. Now the question is, this kind of equation of state, my claim is, shows that there is a ferromagnetic paramagnet to ferromagnetic phase transition if you examine what this equation of state does, and the behavior near the critical region would be very similar to that of a fluid near its critical region, near the vapor liquid transition. This is our target, to show this. So let us examine this equation here and ask what kind of magnetization you have. It is an implicit equation, so you cannot solve this explicitly in an analytic form, because on the left hand side you have a polynomial, on the right hand side you have a transcendental function. So you can do this numerically for various values of H, but our primary interest is to find out if there is a magnetization which is not 0 when the field is 0. If you recall the H versus M graphs for a paramagnet, M divided by n mu, for a paramagnet these got saturated in this fashion, and for a ferromagnet we know that the behavior is something like this, and then there is a hysteresis loop, it comes back and goes off. But now we should ask whether this hysteresis is taken into account in this model or not, and the answer is not in general, because we have to ask where hysteresis comes from, and the way it arises is when you have a complicated substance like a real magnet in the bulk, there are little magnetic domains in this sample, and hysteresis occurs due to the existence of these domains. These domains take some time, they click into place, they click into right orientation, the magnetization inside these domains clicks into the right orientation once the field becomes sufficiently strong. If you have a single domain specimen, there is no hysteresis, everything behaves exactly the same way, and then either there is an up magnetization or a down magnetization. So we will talk about hysteresis separately if time permits, but let me ignore hysteresis and talk about just a single domain specimen, in which case below the critical temperature the magnetization does this, and then the rest of this loop is lost, this portion is present, and then it jumps again. This avoids hysteresis. Remember that the original, if I simply continued with the way the paramagnet would behave, this is what it would do. Let me draw this again. You have a situation where the slope goes like this is h versus m. I decrease the temperature, then the slope becomes steeper and steeper. Presumably at some finite temperature called the Curie temperature, instead of t equal to 0, this slope becomes infinite. It does this, and what would you expect it to do below that? If this is a continuous process, I would expect the curve after that to start doing this, to simply tilt over, but this now would create a problem, because this region of the curve from here to here is unstable. It has the same problem that the PV graph had when you went up, when you came down to a minimum, you went up to a maximum. Between the minimum and maximum, if you increase the pressure, the volume increased, and that was unphysical. In exactly the same way, this region is unphysical completely, because you are increasing the field in the positive direction and the magnetization is increasing in the negative direction, and that is unphysical once again. So this portion is removed, that leaves you with this, which is precisely what hysteresis is. So you have this kind of behavior and then a jump and off there. But now I am saying, just as we had the Maxwell tie construction which got rid of hysteresis in the fluid, here if you look at a single domain specimen, then of course there is no hysteresis, and all that happens is that this curve comes along like this and jumps discontinuously and goes here, and on the return path it does exactly the opposite, retraces the path. So this is what happens in a real ferromagnet. There is, however, a critical temperature at which this linear graph becomes a higher order graph here. There is an inflection point, and after that this thing separates out in this fashion. I will talk about the free energy and show you how this mechanism operates, but as you lower the temperature further, it keeps doing this till it hits the saturation magnetization at very low temperatures. As you approach absolute 0, it is clear the slightest positive field, because thermal agitation is so unable at very low temperatures to destroy the order, causes the magnetization to be ordered in the direction of the field, and in the other direction the smallest negative field will cause complete order in the other direction. So this is what the family of isotherms is going to look like, the analog of what happened in the liquid gas case. The only difference is all those isotherms which in the liquid gas case did this, there was a critical point, and then there was this, and then there was this, and so on. All these graphs are now collapsed onto a single line, and they are collapsed onto this line here. Okay. That is the only difference, because of a certain technical reason which I will explain. There is a symmetry in this problem which is missing, at least overtly, in the other problem, and this is the reason why all these graphs have kind of collapsed. So this is the family of isotherms, the analog of the family of isotherms there. Our job is to show that this critical isotherm, which has an inflection point here where the slope is 0 and the curvature is also 0, exactly the same thing would happen on the critical isotherm which does this. So you can see if you tilt this by 90 degrees, it has exactly the same sort of behavior there. This is our task, to show that at the critical point you do not have a linear behavior here, but you have a higher order behavior. In fact, in the simplest model it will be cubic behavior, because it must be an odd function, so the next thing is a cubic, and after that it splits off and becomes discontinuous. So this is the picture we would like to explain, Now what would happen if I plotted the same graph now, but with T here and M here, then if at some small positive value of the field I plot all these lines, these intercepts here, I get a graph here as T decreases of M versus T, and of course it will hit saturation eventually. So if I start here and plot all these graphs from the smallest value to the largest, from very very high temperature to very low temperature, the graph would start looking like this. If I did it here on this side for a magnet in which the magnetization is downwards, that graph would look like this. It would be symmetric, it would look like this. Okay. On the other hand, if I plotted only these intercepts here, that is the magnetization in the absence of an external field. There are two possible branches, either I have an external field which is switched off from the positive side or from the negative side, and because of this discontinuity I have two branches to the curve, and those would start at 0, important, it starts at 0 field and then it goes up in this fashion. So it is clear that that graph would come along like this. At this value Tc it would start taking off and then hit saturation on this side and hit saturation on this side. It is completely symmetrical, I may not have drawn it accurately, but it is totally symmetrical. This graph here is M in the absence of a field H equal to 0, and this too is M in the absence of a field. Okay. But this thing here, this branch would correspond to a ferromagnet, and let me call it ferro up to show that it is the positive direction, and this is ferro down. So we have two phases, earlier we had a liquid and a gas, but now you got a ferro up and a ferro down. Here is the critical temperature, also called the Curie temperature for magnets, and above that it is a paramagnet. So the critical point is here, and the analog of this is the V versus T diagram here. So this is P versus V, and this graph very loosely is of this kind. This is equal to Vc and this is equal to Tc. So you can see that this graph is more or less getting reproduced there, except that here there is tremendous asymmetry. This curve is not a parabola or anything like that, because we know in reality this here, the small volume thing, is a liquid, so that does not change all that much, and this is gas, that changes a lot, the volume of the gas changes a lot with the temperature, but then the volume of the liquid does not, and it is an unsymmetrical curve, but our focus is at this point here where it turns around, and that is parabolic, and I am going to establish that it is actually parabolic, it goes like a square at that point, and exactly the same thing happens here. So this line of phase, now the third graph we have to draw of course is the P versus T diagram, and that we already drew. So here is T, here is P, this was liquid, this was gas, and this was the critical point, this was Tc and that is Pc, the critical pressure. The question is, what is the analog of that in this graph here, H versus T, what is the analog of it? So that is what we have to figure out, and since H can be positive or negative, we need to have a graph which goes both up and down. So here is H, here is T, and here is Tc, and what is the critical value of the field at which this transition takes place? Obviously 0, because to go from a ferro up to a ferro down you need to switch the field from up positive values to negative values, and therefore this is also Hc. Hc is 0 itself, the critical value is 0 itself. Now what is the analog of this graph? This is a graph of first order transitions, discontinuous phase transitions, where the volume changes discontinuously as you go from the gas to the liquid or liquid to gas. across this line you have a change in volume, an abrupt change in volume, and that is why it is a discontinuous transition. But when you hit this point, the difference in volume goes to 0. This is the difference in volume and that is going to 0 at this point, and then you have a continuous phase transition at the critical point. The same thing happens here. When you are here to here, if you switch the field, if I am here at this value of the field and that is the magnetization, if I take a small negative field, this is the value of the magnetization. So there is a jump from this point to this point and it is discontinuous, and it continues, it goes on being discontinuous till you hit the critical point when the change in the magnetization goes to 0 at this critical point. So this is also a continuous phase transition because it comes along like this and continuously moves out of this point to non-zero values. So again a line of first order transitions ending in a critical point, but what is that line? It is clear by symmetry up and down are not distinguished in this problem completely. Whatever configurations you have in the magnet when the field is up, some regions would be, some magnetic moments would be up and the rest would be down. On the average there is an up magnetization. If you reverse the field there is exact symmetry. So whatever was up is now down and whatever is down is now up. For every configuration for which you have some spins up, some moments up and the rest down, there is an equal and opposite configuration of the same energy in which the whole thing is reversed. Therefore by symmetry it is clear that the line of transitions is this itself, it can't be anything else. That is the line across which there is a phase transition. This phase is ferro up, this phase is ferro down, and on this side is a paramagnet. The analog here is a gas, a liquid and a homogeneous fluid on this side, and in the P versus T diagram also on this side you have a liquid, gas, and on the right of it here is a homogeneous fluid. So this is the analogy, but now we have to answer the serious question, how come the slope here was positive but the slope here is flat of this curve of first order transitions? Well, by symmetry we have argued that this has to be flat, but it is better to see this in a slightly more systematic way or rigorous way. What is the slope of this graph here? What is the slope of this curve given by? This is the boiling curve of the system. It tells you the way in which the boiling point changes, increases as you increase the pressure. And what is the formula that gives you the boiling point as a function of the pressure? Yeah, Clausius-Clapeyron equation. And what does that equation say? It says dP over dt equal to, well, dredge your memories. Pardon me? Says there is a latent heat somewhere, right? Latent heat, so what is the formula? Yeah, the formula that is typically given is that it is the latent heat divided by the temperature multiplied by does something like this ring a bell? Yes? Yes or no? Yes, no. How did you get through grade 11? L is the latent heat of boiling or whatever, vaporization, latent heat of vaporization. How much is it for water? In some units. I do not know what units you use these days. 540 calories per whatever. Okay. So that is the latent heat, this is the boiling temperature, and this is the difference in volumes between what and what? How do I know this is gas and that is liquid? How do I know the slope is positive? Now we are arguing in circles. If you know the slope is positive, then the denominator has to be positive provided L is positive. So how do I know which one should I use here, because I know there are situations where this slope could actually become negative. If you looked at the solid liquid transition, then of course the slope could be like this, or in the case of water it is like this, and that is because the volume, the specific volume of water at 0 Celsius is actually greater than that of ice. Ice floats on water. That does not always happen. When a substance freezes it generally contracts, but in the case of water and a few others like bismuth for instance, as soon as it freezes it expands because it gets into a more open structure. So how do I know which phase is which? I mean, you can't tell me this is G. I could have made this L, that G, and then it would become negative. The answer of course is in what do you mean by L? Do you mean the heat supplied or the heat removed going from one phase to another or the other way? So the correct way to write this equation is without ambiguity is to say what is L over T? This is dQ, the amount of heat you supply divided by temperature. So what is that? It is the change in entropy. So really this is delta S over delta V, and you see, you recognize a Maxwell relation here. This is a Maxwell relation, it is one of the Maxwell relations. Delta S over delta V at constant T at the boiling point is equal to delta P over delta T at constant volume. And now there is no ambiguity. When you say delta S, it could be phase 2 minus phase 1 over volume 2 minus volume 1, or it could be volume 1 entropy 1 minus entropy 2, it does not matter. You have to tell me what is the initial state, what is the final state, and then this delta S is well defined, no ambiguity anymore. Now with this, in our case we could write this as equal to S liquid, let us write this as S gas minus S liquid over V gas minus V liquid. Now you can tell, is this going to be positive or negative and so on. I could have written it the other way, inverting the sign in both numerator and denominator, it will not change anything at all. Is this bigger than that? Yes indeed, because the gas is highly disordered and therefore its entropy is much bigger than that of the liquid. What about the volume? That too is always positive. The volume is always, this difference is always positive. You have two large numbers and this difference is enormous, huge difference in the denominator. When water gets into steam at room temperature, by how much do you think the specific volume changes at boiling point at 1 atmosphere? By how much do you think, by what factor do you think the volume changes? Yeah, 1600 or something like that, it is a huge change, and similarly the entropy. So the slope here is very small because you have a large denominator, both numerator and denominator are positive. If you did the same thing for this graph, if you did the same thing for the liquid solid transition, then dP over dt equal to S liquid minus S solid or crystal over V liquid minus V solid. Now what do you think is happening? Is this positive or negative? It is always positive because the liquid has a higher entropy than the solid, which is an ordered state and has lower entropy. But you see the denominator would depend on the interactions and the structure. In most cases V liquid is greater than V solid, but there are exceptions where V liquid is smaller than V solid, like water, because water is trying to now crystallize in an icosahedral order near 0 Celsius. It is very close packed, but icosahedra can't tile 3-dimensional space, so it ends up, because of the nature of its bonds, freezing into an open structure, and that open structure is less dense than that of water, which had incipient icosahedral order, and therefore V solid becomes bigger than V liquid, and then you end up with the negative slope, a very high slope, because this difference is always small. Liquids are practically incompressible, this difference is very, very small, and therefore the slope is very high, but the sign of the slope is not determined. It depends on what happens to this difference in volumes. Okay. So that is the reason for what is going on there. What would be the analog here in this case? Well, I would have to write dH over dt over delta M, and now the point is, when you have a ferromagnet in this state up there, and here is your ferromagnet. Most of the stuff is like this, magnetic moments are like that. Well, here and there are guys like this, but on the average it is up. And now the down, this phase would have exactly the opposite. Whatever is up is down, and whatever was down was up in this fashion. There is an exact symmetry between these two configurations, and therefore for every such configuration possible you have one such configuration possible there, and therefore the entropies are exactly the same. On the other hand, the change in magnetization is different, is non-zero, it is from here to here. So you have a situation where the denominator is non-zero and the numerator is 0, and therefore this is equal to 0. So that is the reason why the ferro up to ferro down coexistence curve has a flat slope. It can't have any other slope, because if it had a slope like this it could not end at this point, and besides if it had a slope like this there is no reason why it should have a slope like that, because they are completely symmetric between up and down, and the only graph that is completely symmetric is in fact the flat curve. And that is a good thing too, because you see if you start here at this pressure and I want to make it a gas, what should I do? There are two ways of doing it. One of them is I lower the pressure keeping the temperature constant, otherwise I heat the system keeping the pressure constant. I keep it in an open beaker and I heat it. So I follow this path, and of course I cross over into the gas phase out here. If the slope were not 0 here, in principle you could go from a ferro up to ferro down by starting here and simply heating it. Now who ever heard of heating a magnet and making the change of magnetization change direction? It can't. You have to cross this line, and therefore it is obvious that this slope is indeed 0, and this is the curve, this is the curve here. Now you could ask, with this analogy so close, how come there is so much asymmetry here? And the answer of course is these phases are very different phases in some sense, but there is a very interesting law called the law of rectilinear diameters, which says there is a change of variable possible here. So instead of V I have a change of variables, a linear change, such that you have a parabolic shape here, it becomes curved. So there is indeed some line here about which there is a symmetry of this curve, and that is an experimental fact. There are theories to explain why this should be so and so on, but they become model dependent, very model. Right now we are trying to see what can be said without any model dependence, but this is what is going on. So we have now, I believe, complete analogy between the two situations, the 3 graphs here and the 3 graphs here, and our task is going to see what is the behavior near the critical region. But before that, let me show you from this graph itself, we started doing this, that you do get behavior of this kind for the zero field magnetization, because if I let m at h equal to 0 be m0, let us just denote it by m0, this guy here is the so called remnant or spontaneous physicists like to call it the spontaneous magnetization. Okay. It is the magnetization that you get in the absence of a field. In the ferromagnetic case it is non-zero. Okay. We would like to ask, can we derive an expression for what this intercept is going to be like, and the answer is very simple, because if I do that, if I put m equal to if I put h equal to 0, then m naught over n mu equal to tan hyperbolic lambda m naught mu over n k Boltzmann T in this case, and let us give it a symbol. Let us give it, let m naught over n mu be equal to m naught, magnetization per atom per moment in units of this natural unit mu. Then what does this become? This equation becomes m naught equal to tan hyperbolic and mu squared lambda m naught over k bt. That is the transcendental equation we have to solve, and that is easily solved. We do this numerically, we plot m naught here versus whatever is on the right hand side, and this is the line m naught, the 45-degree line, and you have to plot the right hand side, and we know that this saturates at m naught going to infinity, plus minus infinity, it saturates at plus minus 1, but the slope at the origin is mu squared lambda over kt. So there is a case, this is the saturation, so there are situations where the curve goes like this, and this is for t greater than Tc, and for t less than Tc the curve would go like this, and therefore you would have a root here and a root there. They would correspond to the two intercepts that you have, this intercept and this intercept here. When would that happen? If you lower the temperature sufficiently, there is one curve where the slope is exactly 45 degrees here and goes off, and after that it splits off, the roots split off, and that happens when the slope is 1. So Tc given by the condition mu squared lambda over k Boltzmann Tc equal to 1, or Tc equal to mu squared lambda over k Boltzmann. It is non-zero. So at that point, for temperatures below that, the slope gets higher than unity at the origin, and you have two non-trivial roots. The root in the middle continues still, so it is like saying this root still continues, this is m naught and this is m naught, but this root still continues, and our job is to show that it is actually unstable. That root is not a thermodynamically stable state, because that would be the paramagnetic branch, and now you have gone into the ferromagnetic phase, so the paramagnet becomes unstable. Now how do we do that? We can't do that from here, you really need to do that by asking what is the free energy of the system, and that is where the Landau theory of phase transitions comes in, and I will mention that next. But this is the mechanism should be clear, and incidentally you can play with this and do the same graphical construction even with h small positive or small negative, and you would end up with these curves. So just purely numerically it is easy to deduce these guys, but what is interesting is that the critical temperature in this model depends on this constant lambda, and this lambda was the multiple of m naught in the model that I chose for the effective field, this thing here. So while here it is completely empirical, you just chose the internal field to look like this, any microscopic model of magnetism should be able to predict what this lambda is or what it is replaced by. So the job would be to try to find this quantity here, but notice that I also removed this n in order to make things written in terms of intensive variables, but that is a small technical detail. The fact is that there exists a non-zero critical point, a non-zero critical temperature below which you have ferromagnetic order. So that is the first lesson we get from here. The next thing we have to do is to find out what is the behavior of this graph, because this looks like there is a cusp here, and I would like to know what does this cusp do, I mean what sort of behavior do you have at this point, and similarly what kind of behavior you have for the susceptibility. This thing is suggesting very strongly that the susceptibility, which is the slope at the origin, is actually going through infinity, because there is a stage at the critical temperature when the susceptibility becomes infinite, the slope is 90 degrees, but after that on the other side you can still continue to define the slope, you can still continue to define the susceptibility as chi t equal to delta m over delta h at h equal to 0 at constant temperature evaluated at h equal to 0. You can continue to define this even if the function is discontinuous, m itself is discontinuous, but its slope is could be defined very well, because you see the slope here and the slope here by symmetry are exactly the same. So there is no problem with defining the right slope or the left slope, and you get exactly the same number on both sides, but meanwhile the susceptibility would go off to infinity. So if I plotted the susceptibility as a function of temperature T and I plot chi T, at the critical point this guy goes off in this fashion, and the claim is below that it will fall once again in this fashion. Okay. We would also like to derive the Curie-Weiss law from these relations. So let us see how to do that. So we look at this equation of state and see what we can do. There are several things we can do, the first of which is to actually find out what this solution to this equation is. So let me write this in a slightly better way, m naught equal to tan hyperbolic mu squared lambda over kt m naught, but mu squared lambda over k is Tc. So we could write this as Tc over T m naught, write it in this fashion, because Tc has now become a parameter. Instead of constants mu squared lambda k Boltzmann and so on, we just replace it with Tc. So it will tell me the behavior near to equal to Tc. Okay. So it is obvious the solution to this at T equal to Tc, this cancels, the only solution to m naught is tan hyperbolic m naught is 0 itself, but below Tc you have other solutions, and the question is, can I extract those solutions, can I see what those solutions are, what should I do? I am going to keep T slightly less than Tc, so the slope is slightly greater than 1. Now what should I do? Pardon me? Expand this, because I know I am in the region where the magnetization is essentially 0. I am in T, here is Tc, and I am here in this region near, this is m naught, near 0 and near Tc. In that region I can expand this, because T is approximately Tc, it is a little less than that. So Tc over T is a little bigger than 1 and m naught is approximately 0. I should expand this function. What should I do? And then what should I do? What would be the next thing? Well, a correction, this would be a higher power of m naught. Now what would that correction be? Pardon me? Cubic, plus or minus? How are we so sure it should be minus? Minus is right, how am I sure it has got to be minus? Well, the plus would keep going, it is coming down, right, it is going to get saturated, so there has to be a minus sign. So the next correction would, of course, otherwise it would keep increasing. So there is a minus, minus what? What should it be proportional to? All right, that is a constant, 1/3, yeah, that is a good guess. Well, cot hyperbolic, remember, was 1 over x plus x over 3, so tan hyperbolic is very reasonable to think that it would be something like this, and then what? Cubed, this whole thing cubed, okay, Tc cubed over T cubed m naught cubed, and I want the solutions of this equation. I want these two roots, this guy is always a root, I want the root here and the root here, those two. So what should I do? Can I cancel m naught? Yes, because I want the root other than 0. So this says m naught times 1 minus Tc over T is approximately minus 1/3 Tc cubed over T cubed m naught cubed, and I cancel the m naught, so this is squared. Remember, this is a negative quantity because T is a little less than Tc, so let us get rid of that by writing this, getting rid of this plus sign and writing it as Tc over T minus 1 in this fashion, which is Tc minus T on top divided by T. This is this guy here. So what lesson does it tell you finally? Well, this is harmless, this guy is fluctuating is around Tc, so you can essentially set it equal to Tc. The point, the place that is going to 0 is this. This factor also is essentially unity apart from higher order corrections. So what lesson does it tell you? What does it tell you about m naught? It implies that m naught is proportional to plus or minus Tc minus T to the power half, the square root singularity. Therefore, what is the slope of this graph? What is the slope of this graph at this point? It is 90 degrees, it is 90 degrees because it is a square root. If you differentiate, you get a 1 over square root which explodes. So you really have this and you really have this. That is the nature of the singularity at that point. This half is called a critical exponent. In this case it is called the magnetization exponent because that is what the spontaneous magnetization does. Exactly the same thing is true for the liquid gas case. I am not going to prove this, I will give it to you as an exercise to start with the van der Waals and then show that in the volume versus temperature graph in the vicinity of the critical volume, this difference here vanishes like the square root of the T minus Tc, Tc minus T, same half. So while you know that the gas becomes a liquid due to some different mechanism totally different from what a magnet does, the half is exactly the same in both cases, and the half is a function arises here because both these models are examples of what are called mean field theory models. In other words, in the van der Waals case we assumed that the pressure was not P but had a correction minus A over V squared because of the attraction between the molecules. But that attraction we said was every molecule seals every other molecule, on the average it has a force, an attractive contribution proportional to the square of the number density, that is how you got a 1 over V squared. In the same way here we assume every magnetic moment is seen by every other magnetic moment and the internal field at any point is proportional to the magnetization itself. So we had exactly the same philosophy and that is what led to the same critical exponent. Now the question is, does the experiment show this or not? And now you have to ask, how accurately can you get to the vicinity of Tc and control your temperature to see this, and the answer is yes. In most cases, depending on the experimental setup, you would see essentially something like half, but the unfortunate thing is if you do careful experiments near Tc, then you do not see a half here at all, you see something which is very different in many cases. You might see a 1/3 or 0.3 or something like that, which is quite different from a half, but you have to get very close to the critical point to do this. How close should you get? There are precise criteria for it. Now it turns out temperature is one of the hardest things to control, you can't be very accurate with temperature. To control temperature to a millidegree accuracy is a very big achievement already. Going below that to higher accuracy is even harder. Unlike other quantities like frequency, frequency is the most accurately measurable physical quantity. You can measure frequency to 1 part in 10 to the 15, it is just incredible things. There are clocks out there, there are astrophysical clocks, astronomical objects whose there are pulsars whose rate of change of time period can be computed to 1 part in 10 to the 19 and they maintain it. So those are very accurate clocks, but temperature is notoriously fickle, very difficult to control temperature. But depending on the system, I will say more about this, you can determine what the critical exponent is, and it turns out that this exponent is not quite half. But for the moment let me retain this half as a mean field critical exponent, mean field. Okay. The first such exponent, we are going to talk about more of them. The next question is, how does the critical isotherm behave? we know the critical isotherm in the fluid magnet case had it had a inflection point. So we know the following is true. We know that here is V, here is P. This isotherm had an inflection point. At this point delta P over delta V at constant T was 0. This is at Tc. d2P over dV2 at constant T was 0. It is an inflection point. So you had something which came along like that and did this. Now I am not going to do this again, but I leave you to show that if in the vicinity of this point, which by the way is V critical and P critical, if I define little p to be equal to P minus Pc and I make it dimensionless, little v equal to V minus Vc by Vc, and shift origins to this point, then this is like saying this is V and this is P out here, and I ask what does this curve look like at that point. Then it is easy to see it is not linear, it is coming down, has a flat behavior and then goes down. So it would look like P is proportional to V cubed, because after linear the next one would be a cube, and you can show this from the van der Waals isotherm by actually computing Pc, Vc, Tc and then going to these reduced variables, doing the expansion of the equation of state and so on. You can show that P goes like V cubed. So this fellow here, or V goes like P to the 1/3 this side. This 3 here is also a critical exponent, and in this case a mean field critical exponent. It is a cube, it is a 3. In general it is something else, and the standard symbol for that critical exponent is delta. In the theory of phase transitions there have been a whole lot of critical exponents have been identified and fixed names have been given to these exponents. That one is called delta, this one here is called beta, and it is not the inverse temperature, they just ran out of symbols, so they use this thing here. It is a critical exponent, and in mean field beta is a half, delta is a 3. In reality delta could be something different and could be 5, it could be 8, it could be larger and so on. So you have again a correction to mean field exponents here. And the question is what does this critical isotherm of ours do in this case? Well, that is, we have to look at this. So we go back here and let us try to rationalize this damn thing, so that I put m equal to m over n mu, this becomes m equal to tan hyperbolic mu over k Boltzmann T h plus lambda mu m, is that correct? Okay. And let us take things out so that we have a lambda out and a mu squared. So I take this out here and h divided by lambda mu plus m, this fashion, and this is equal to tan hyperbolic. Now lambda mu squared over k I believe was our Tc, so this is once again Tc over T, let me call this little h plus m. So this h over m mu I call little h in some units, it is just the magnetic field, but let me write it in this fashion. The critical isotherm is given by m equal to tan hyperbolic h plus m, because T equal to Tc on the critical isotherm. And what am I trying to do? I am trying to find in the h versus m graph I know the paramagnet looks like that and I know the ferromagnet looks like this, but the critical isotherm looks like this, and I am trying to find this cubic singularity here. So this is at Tc, that is at Tc, and I am trying to find and trying to show you that it is also a cubic curve from this graph, from this equation here. Now both m and h are near 0, so you write here in this region the critical value of the field that we already saw is 0, Hc is 0 and m critical is also 0. So therefore this is equal to h plus m minus h plus m whole cubed over 3, and that is m on this side. So what is the conclusion? This m cancels on both sides and the equation you have to solve is precisely the earlier equation. It says therefore that m plus h cubed goes like h itself, and both m and h are small, okay. And you solve this equation, you discover that this is even smaller, this guy here. So keeping to first order terms here, it immediately is clear that you can neglect this and you get m cubed is proportional to h. Of course you can refine this and go ahead etc., but our point is not that. Our point is to show that at the critical point you have a cubic behavior. So it is exactly the same. The same 3 appears here as appears here, even though these are very different systems, altogether different systems. This is not an accident. Yeah. Well, work this out, I mean now do this consistently, solve this equation consistently, near h equal to 0, m equal to 0, solve it consistently, and then you discover that h goes like m cubed, so it is much smaller, right. Okay. So the mean field, the exponents have come out to be the same for 2 different systems altogether. We had no reason to expect this at all. By the way, what does the susceptibility do? And that is not hard to find, because all you have to do is to find the slope of this graph at this point and go back to this equation here. For t slightly greater than Tc, t slightly less than Tc, find the slope of m versus h by solving this equation, and you will discover that chi t is proportional to 1 over modulus t minus Tc with a power 1 in exactly the same way that you will find here on this graph on this side. What is the analog of the isothermal susceptibility? The isothermal compressibility, and you will discover kT equal to minus 1 over V delta P over delta V at constant temperature, and you know that this fellow goes to 0 and therefore the reverse of this guy goes to infinity. It is exactly the same, also has the same 1 over T minus Tc behavior. In general, however, this is not 1, this is the Curie-Weiss law, we have derived it now, but this is not 1, but it is a critical exponent and it is generally denoted by gamma, not the ratio of specific heats. This gamma experimentally for 3-dimensional magnets could again depend on the kind, depends on the kind of magnet you have, it is of the order of 1 and 1/3, about 1.3 or so, not 1, not 1. So there is a deviation from the mean field critical exponent which we found here, again for deep reasons, but mean field will give you in a very simple way this quantity here. Our next task is to find out where are all these things coming from. Is there a simple phenomenological theory we can give to see when the phase transition would occur? What would be the general way of doing this, including all these systems together, and this is what Landau did, and I will talk about it next time, which is tomorrow. Landau's theory of phase transitions, and he did this way back in 1937. and he actually showed that ideas following from broken symmetry could lead to predictions of these phase transitions, or at least an analysis of these phase transitions. Today the starting point for the modern theory of critical phenomena is Landhaus theory. This is the starting point, it is a phenomenological theory, and from that we get all the stuff that we put in and so on. So it has been elaborated upon, it has been improved upon, and then renormalization group method is a takeoff from here, from this starting point. So it is a good idea to have this empirical theory simply because it applies in so many different fields, and I will do that tomorrow.